Every year, China produces enough oyster shells to bury small cities. Mountains so vast their stench carries for miles, leaking toxins into air and water. But when coastal waste collided with dead, acidic farmland and a 70% crop collapse, scientists took a risk. They buried millions of these shells into the earth itself. The results changed everything, except for one crop that mysteriously failed. Why did this desperate move create both a miracle and a new mystery? China pulls more oysters from the sea than any other country on Earth, almost 12 million tons every year, accounting for 80% of the global supply. For every oyster harvested, nearly all of its mass, about 90%, ends up as shell. These shells do not simply disappear. They pile up along the coasts of Fujian and Guangdong, forming what locals call the White Mountains. The scale is staggering. Year after year, these mounds grow higher, with each shell taking 50 years or more to break down naturally. The air around these mountains is thick with the sharp, rotten smell of hydrogen sulfide and ammonia, byproducts of slow decay and bacterial action. Toxic gases drift into nearby towns, and waterways choke with runoff. The waste is so persistent and overwhelming that even industrial-scale processing plants can only scratch the surface. One facility processes just a fraction of the 11.9 million tons generated each year. The crisis stretches far beyond the coastline, setting the stage for an even deeper disaster inland. Inland, the crisis took on a different form. Fields once known for lush longan orchards and rows of chives began to fail. Soil tests revealed pH readings as low as 3.8, levels so acidic they rival lemon juice. Roots struggled in ground that had turned dense and unyielding, with a texture closer to cement than living earth. Farmers watched as longan trees dropped their fruit before ripening, and chive harvest shrank by nearly 40%. The air carried a sense of loss, not just from failed crops, but from the knowledge that the land itself was slipping away. According to a 2021 government report, 70% of productive capacity had vanished in just 15 years. One longan grower described it simply: the trees stopped growing, the soil was dead. With every season, the need for a solution became more urgent as livelihoods and food security hung in the balance. Inside the industrial park near Huyen, a line of conveyors moves mountains of oyster shells toward a massive rotary kiln. Here, the shells are heated to 473 degrees Fahrenheit, hot enough to destroy bacteria, neutralize lingering ammonia, and break down organic residues. The air inside the plant carries a faint mineral tang, a sharp contrast to the sour stench outside the shell piles. After baking, the shells are ground to a fine, chalky powder. Each ton contains not just calcium carbonate, but also magnesium and iron, elements essential for soil recovery. The facility can process 264 million pounds of shells every year, a fraction of the waste generated along China's coasts. According to the plant manager, the goal is clear: turn a public health hazard into a resource for agriculture. The resulting powder, known as ocean biolime, is bagged and shipped inland, ready to be spread over fields where crops once failed. What happens next will test the promise of this engineered solution. In the orchards and fields where crops once withered, the first season after applying ocean biolime brought a visible turnaround. Longan trees regained their canopy and began producing full clusters of fruit again. Chive harvests, which had been cut nearly in half by acidic soil, surged by 60% compared to untreated plots. Farmers described the soil as softer, easier to work, and no longer sour to the touch. Lab tests confirmed what they saw. Soil organic matter increased by 48%, and available nitrogen rose by 69%, restoring the nutrients that had been stripped away over years of decline. Revival was not limited to a single crop or field. Across trial plots, beneficial bacteria returned, breaking down organic residues and rebuilding the living structure of the soil. One lettuce crop grown with shell powder instead of chemical fertilizer was calculated to reduce carbon dioxide emissions by over 12,000 pounds, a figure based on transparent accounting of fertilizer production and soil carbon gains. For many growers, these numbers meant not just recovery, but hope that dead land could truly live again. Not every crop responded as expected. In fields planted with peanuts, yields dropped after the first application of ocean biolime. Agronomists traced the problem to the unique biology of legumes. Peanuts depend on symbiotic bacteria in their roots to fix nitrogen from the air. When soil pH shifted too quickly, these bacteria were disrupted, leaving the plants unable to access enough nitrogen. To prevent this, experts now recommend a phased application, raising pH by no more than half a point per month and waiting several months before sowing legumes. Safety protocols also require every batch of shell powder to be tested for heavy metals before use. Even as most crops thrived, these exceptions underscored the need for careful monitoring and crop-specific guidelines. Along the southern coast near Hong Kong, the collapse of oyster reefs had erased nearly 85% of their original footprint over the last 150 years. In response, marine ecologists from Hong Kong University revived centuries-old wooden stake methods, creating new surfaces for oyster larvae to settle. Within a year, restored plots supported 61 distinct species, a more than twofold increase in biodiversity compared to untreated mudflats. Total biomass on these reefs jumped tenfold, signaling a dramatic return of marine life. Each mature oyster now filters up to 8 gallons of seawater an hour, clearing algae and pollutants and helping to restore water clarity across the bay. Oyster shells are driving a surge in green technology far from the southern Chinese coast. At Hiroshima University, researchers credit shell powder for antibacterial coatings now used in Japanese hospitals and food plants. Tests show these paints wipe out 99% of Staphylococcus aureus on contact. In water treatment labs, the same material removes up to 95% of lead and 87% of arsenic from industrial wastewater, providing a low-cost fix for heavy metal pollution. Material scientists have blended shell powder into biodegradable plastics, boosting strength by 12% and opening the door to alternatives to petroleum-based packaging. Engineers are building carbon-capturing air filters around the unique structure of ground shells, while road builders in coastal cities mix shell powder into asphalt for better grip and longer-lasting surfaces. These advances form a blueprint for turning waste into value. The next steps are to expand pilot processing plants to new provinces, set strict soil monitoring protocols, and share restoration models internationally. Full data and protocols are available in the appendix, inviting policymakers, scientists, and entrepreneurs to test, verify, and scale what began as a local fix into a global green solution. Millions of tons once poisoned land and water. Now they are a test case for global waste, proof that what we bury can either destroy or revive the world we inherit. What would you choose?